Okay, so welcome to today's lesson. We're going to talk about graphing cube root functions. Many of the same steps we did yesterday in graphing square root functions are going to be followed here today. Slight variances will occur, so let's get right into it. All right. Our parent function of all cube root functions, our f of x, is equal to the cube root of x. There's no h and k values here. Our a value is equal to 1. Our h value is equal to 0. Our k value is equal to 0. Okay? We have a point of symmetry, and our point of symmetry is always going to be at, for these, 0, 0. The cube root of 0 is 0, and everything will kind of have symmetry around that point. Okay? So let's go ahead and graph this thing using our graphing calculator first. Okay? To get there, we're going to hit Math. Let me actually show you the keystrokes we'd have to do here. So I'll clear that. We're going to hit Math. We're going to go down to our fourth option here, and that shows us how to get cube roots. So going back to y equals, going to Math, option 4 gives us the cube root. Okay? Now, from there we just know it's the cube root of x. Okay? We're going to go graph this. The easiest way to graph this is go to Zoom 6. That'll give us a symmetrical graph. And we know that our graph, as we look at it, it's increasing slowly but surely, and at this point then, it remains increasing, but it's increasing at a decreasing rate. It's much slower, okay? And if we look at it, there's a point of symmetry kind of right along this axis. And so we'll kind of see that, all right? We kind of look at it, it looks like it's somewhat symmetrical, okay? All right, and that's going to go through the point 0, 0. If I go to my table now, I can go to second graph and look at my table. Clear that line off there. I see that I go through a number of points here that I can graph. I see I have the point 0, 0. I can graph that. I have the point 1, 1, which is right here. And I'm just going to focus on graphing points that are easy to graph. So -8, -2. -8, -2 is right down here. And since there's going to be symmetry, I'm probably going to have +8, +2. And I see that as well. Okay? So +8, +2. If I graph this, I've got these 4 points to go through. And there we go. Now on a cube root, I can take the cube root of any number, both positive and negative. And we see this in this graph here. But if I take the cube root of -8, I realize that this cube root of -8 can just be written as the cube root of -2 times -2 times -2. So I can take the cube root of negative numbers, whereas I can't take the square root of a negative number. That gives me imaginary numbers. Therefore, all values of x work. Since all values of x work, my domain, written in interval notation, would be -infinity to +infinity. Since all values of x work, and we have our interval notation -infinity to +infinity, our set notation for domain then is a set of all x values from -infinity is less than x, which is less than infinity. That's our set notation. Our range, again, we're dealing with y values. Well, our range, we're going to continue to go up in our y values as x becomes positive. As x becomes more negative, our y values will continue to increase. So we're basically going to have all values of y. And thus our domain is going, our range will also be from -infinity to +infinity in interval notation. And for set notation, we're going to have the set of y values from -infinity less than y, which is less than positive. So really our domains are always going to be from negative infinity to positive infinity, and our ranges are going to be from negative infinity to positive infinity when we're dealing with cube root functions. Okay. Now again, I said this is the parent function. Every other function is then going to be some kind of transformation or compress or expand kind of situation from this parent function. F of x is equal to the cube root of x. Now again, so we're going to take a look at our transformations right here. And we're going to focus on the three parts of the transformation. Our first value out here is our a, and that's either going to stretch or compress, or possibly reflect our parent or our function. Our h values, again, the h values are always under, they're either in parentheses or in this case under the radical sign. That's a horizontal shift. We know that minus h shifts things to the right. We know that plus h shifts things to the left. We know our vertical shift. When k is greater than 0, it shifts things up. And when k is less than 0, it shifts things down. So we're familiar with this. We know the reflection occurs when a is less than 0. So when a is negative, And those are typical transformations. Very similar to transformations that you've seen for quadratics, exponentials, and those sort of things. Okay? So let's take a look at these in action now. So we're going to describe the transformations from the parent function, f of x is equal to the cube root of x. Let me make that a little bit bigger so it's clear. Okay? So for problem A, we have g of x is equal to 2 times the cube root of x minus 3 plus 5. So let's look at our transformations here. The first one is that a is equal to 2. That's a vertical stretch by 2. So that's vertical stretch by a factor of 2. We're then going to look at our h value. And we see it's minus 3 here. So we have x minus 3, tells us we have a horizontal shift. And that horizontal shift, since it's x minus 3, is going to be the right 3. And then finally our k value here. Our k value, since k is equal to 5, is a vertical shift up 5. Okay? So we're going to have a vertical stretch by 2. We're going to have a horizontal shift by moving to the right 3, and a vertical shift up 5. I think it's worthwhile to take a quick look at those graphs. So we're going to do that. I plug both functions into the calculator. My parent function is the first one, and then the transformed function. We're going to take a look how this graph. So I'm going to go to zoom 6. This is my original function. You see it goes through the point 0, 0. It starts out below, and then it goes above. You see now my second function comes up. Okay. Now, a couple things we noticed. We had a vertical stretch. So as you notice, this is a little bit bigger now than the original function in terms of our stretch. We pulled it. It's like we had a string. We pulled it from the top and the bottom to stretch it vertically. We see we move to the right. From this point here, we move to the right 3. And we're also seeing that from this point, we moved up as well to our point of symmetry. We moved up 5. If we go to our table, we should end up going through the point 3, 5. So as I said, we should be going through the point 3, 5 now that we're on our table. And when I look at it, the transform function does go through 3, 5. Originally we went through 0, 0. That was our point of symmetry. We moved to the right 3 and up 5. All right, let's look at B here. I've got h of x is equal to negative cube root of x minus 4. Identifying our a value is equal to negative 1. That means I have a reflection over the x-axis, which means instead of starting below the x-axis and finishing above the x-axis, we're going to see the graph do this. Okay? That's how it's going to look. So that is a reflection over the x-axis. We have no h transformation. H is equal to 0, so there's no shift there. Our k value is equal to negative 4. That means I have a vertical transformation. And it's down 4. Let's go ahead and look at these last two examples here. For m of x, I have the function equal to 1/2 times the cube root of x minus 1. Our a value is 1/2. Well, what does a 1/2 value mean out front? Well, this is a vertical compression. Let's convert vertical compression by 1/2. So this means that it's going to be less tall by a factor of 1/2. So we're going to compress it. If you think about a compressor, a garbage compactor, a compressor does the same kind of thing. It takes something that's bigger and makes it smaller. And you'll see that when I graph this. We also have an h value that is equal to, we have x minus 1 here. That is going to be a horizontal transformation. And that horizontal transformation will be to the right one. Let's go ahead and see how this looks graphically, so we can understand what a vertical compression looks like. Putting this into our calculator, this is what we get, the cube root of x, and we get 1/2 times the cube root of x minus 1. We're going to go graph this. Zoom 6 again gives us a nice, neat graph. Our original function here, going through the point 0, 0, and now we see our next one is compressed. We see it's not quite as tall, and it's not quite as, it doesn't go quite as far above or quite as far below the x-axis. And we also see it's been moved a little bit to the right one. Our axis of symmetry now is more over here, and it's been compressed. It's not quite as tall. For our final example, I have p of x is equal to negative 5 times the cube root of x plus 4. Again, there's nothing outside the radical sign, much like in example 3. So I know I don't have any, or after the radical sign, I should say, so that I know that there's no k transformation. There's just an a transformation. So a is negative 5. This is both a reflection and a vertical stretch. It's a vertical stretch of 5. Because I have x plus 4, this is a horizontal transformation to the right, or to the left, sorry, to the left. Taking a look at this graphically, I've entered in the parent function for y1, the transformed function p of x in for y2. I'm going to take a look at a graph of it. Again, zoom 6, a nice neat graph. This is my original function, cube root of x, and this is my transformed function. We see a stark contrast in how this looks. In fact, what we see here is we see it's a lot taller now. That's my vertical stretch. Should actually be that. Sorry, I'll color it in red. That's my vertical stretch. All right. We see the reflection as it starts up here and it finishes low. It starts high and finishes low. And then finally, we see our transformation to the left by 4. So those are how we do transformation.